Hi everyone. Today's lesson is going to focus on lesson 8B in the new packet, which is going to cover the sequence notation that we were introduced to in the first lesson. As a reminder, all of these lessons are included in the learning plan because you don't have a physical packet at this point. We didn't have time before we left for this unexpected dismissal to talk about how to print out these packets. So as a reminder, you can access all of the packet pages in the learning plan, and you can do one of two things. If you have a printer, you can print the pages of the packet and work on them as if you were working on a regular packet page in the classroom. Or if you don't have a printer, you can simply keep these pages open, maybe in a separate tab or in a separate window in your browser, so that as you're watching these videos, you can follow along with the packet questions, and you can do your work on a separate piece of paper if you need to keep track. Now, the goal for the lesson today is to really just focus on the way sequence equations look. You got a preview of that in lesson 8A, and you started kind of thinking about that in that Desmos activity. So today you'll hear me reference that Desmos activity a couple more times, and specifically I'll be referencing some of the observations that you hopefully made in questions 21 and 22 on page 2. So if you did this lesson before, you may want to refer back to some of the observations that you made, specifically about these new terms called arithmetic sequences and geometric sequences, so that you're familiar with that terminology and hopefully have already noticed some things that can give you an advantage going into the current lesson on page 3. Now, the first question is going to ask you to think about the arithmetic sequences that we encountered in that lesson. If you don't remember any of the sequences, perhaps it's been a while since you looked at it or you don't really have it accessible, I'm going to make a quick suggestion, and you can pause the video if you need to read this little note. You could always come back to this video later if you need to do these things. My suggestion is to find the Desmos link, which was in last Thursday's part of the learning plan. So go back to week 30, find Thursday's assignment, and find the link specifically to Desmos, so that you can follow along with what I'm about to do. I'm going to go back to some of the cards that were part of that card sorting activity in Desmos, and it might be helpful to look back at those cards for yourself so you can see what I'm talking about. If you don't have access to it anymore, that's not necessarily a deal breaker, but I'm just giving you that tip so that if you feel like you need to follow along, you can figure out where I'm getting this information from and you can find it yourself, especially if you need to take more time than just what I'm going over in the video. Now, my goal today is to try to break down why the equations in that Desmos activity looked the way they did. If you successfully did the Desmos activity, and this might look familiar for those of us who did it, hopefully you saw some of the cards that look like this. You can see that I've kind of moved some of the cards off to the side, so I'm really only focusing on a few cards right here, and I'm specifically focusing on cards that we would call arithmetic. Arithmetic sequences are sequences that have an adding or a subtracting pattern. So this sequence, for example, is arithmetic because 7 minus 4 is 3, 7 minus 3 is 4, 4 minus 3 is 1, 1 minus 3 is negative 2, negative 2 minus 3 is negative 5. Notice how I keep saying minus 3, minus 3, minus 3, minus 3? That's arithmetic. It's because to get to each term in this bottom row, I'm going to keep subtracting 3. That number that we keep subtracting is actually important. That number is called the adder. And you might be thinking, well, you're subtracting, Herbert. It should be called the subtractor. We actually just use the word adder to talk about anything that's either adding or subtracting, because technically, subtracting is just adding negative numbers. So anything that's arithmetic has an adder. This is another example of an arithmetic sequence. Take a second before I say anything to pause and look at these numbers. Can you tell what makes them arithmetic? Can you tell what makes them have an adder? Can you tell what that adder is? Think for a moment about that bottom row. 3 plus 4 is 7, plus 4 is 11, plus 4 is 15, plus 4 is 19. This one's arithmetic and its adder is 4. So the adder is the number that makes the pattern go. the number that adds to each value that gives us the next one in the sequence. In case you're curious, the top row of numbers isn't really part of the sequence. The top row actually just tells you which terms in the sequence we're referring to. So we would say in this sequence, for example, the first term is 7, the second term is 11, the third term is 15, the fourth term is 19. That's what the table means. If there's some confusion here about the 0 term, it is a little strange. Like you might think that 3 is the first term because it's literally the first number that you see in the table. But if the 0 in the table suggests that this is term number 0, then we call it the initial value, or term 0. Most people think of the first term as n equals 1. Second term, n equals 2. Third term, n equals 3. Fourth term, n equals 4. So we just kind of have to get used to that idea. The same thing goes for any table. The first term in this one is 4, the second term is 1, the third term is -2, the fourth term is -5. So you can tell that the n just tells you which term number we're talking about. The actual term in the sequence, though, the important stuff, is in the bottom row. So, knowing that that's what arithmetic means, let's focus on their equations for a moment. Notice how in question number, or in this pair of cards, and I'll move these off to the side a little bit, this sequence with the 7, 4, 1, -2, -5 goes with this equation, 7 minus 3n. See if you can figure out why. If you think about the -3, that part might be obvious now that we've seen the pattern, because, because 7 minus 4 is 3, 7 minus 3 is 4, 4 minus 3 is 1, and -3 and -3 keeps connecting all of the numbers. So the -3n is the adder. And every time you look at where the n is in these sequences, you're actually going to see the adder attached to that n. So in this other example, we can tell that the adder is 4. 3 plus 4, 7 plus 4, 11 plus 4, 15 plus 4. And sure enough, in its equation, there's a plus 4n. The plus 4 is attached to the n. This one has the same thing. 7 minus 3, 4 minus 3, 1 minus 3, -2 minus 3. And its equation also has a -3n. So that's something we might want to immediately make an observation about in our actual lesson here. Whenever you're looking at a sequence equation, and in letter A, this is kind of like a blank slate for a sequence equation, the adder is always the number attached to the n. Once you know that, it's going to be a little bit easier to see these equations pop up all the time, because the adder is always the one that's going to be next to the n 100% of the time, and you can get used to that as a consistent thing. Now, the other blank, the blank that goes before it, is something that might be helpful to go back and observe. Let's see if we can go back to some of those cards and connect some of those details there. If I go back and look at some of the cards and notice what's not attached to n, that's the part that I want to think about next. Let's notice 7 and where 7 appears in the sequence. 3 and where 3 appears in the sequence. Do you notice something consistent about both of those? 7 is the 0 term in this table. 3 is the 0 term in this table. It looks like those numbers, the numbers before the adder number, are the initial values, or the 0 terms in their respective sequences. So that's actually something we can conclude. Now, if you're looking at that going, no, Herbert, that doesn't make sense because look at this bottom one, then I want to remind you here, the bottom one actually works too. The bottom one's a little bit tricky, but technically, the bottom one actually is consistent with this pattern. Let me quickly explain, and hopefully you can kind of pick up on my logic here. In the bottom one, and I'm going to try, let's see, hopefully we can get this to show up. There we go. In the bottom one, according to what we think is true, 10 should be the initial value of this problem. And I'm seeing this pattern, thinking this makes sense, so let's see if that does indeed ring a bell. If you look at this list, though, you see how it's missing its table? It doesn't have a table like all the other cards did. Technically, we can give it a table. The first number that they gave me in the list of numbers was a 7. The second term they gave me was a 4. The third term they gave me was a 1. The fourth term they gave me was a -2. And the fifth term they gave me was a -5. So if I think about a table and make a table because the card didn't give me one, then I would use a little bit of logic and say, oh, wait a minute, hold on. The 0 term is the initial value. The 0 term is the one I want. So let's use a bit of logic. If subtracting 3 is the pattern, then we should ask ourselves, well, what -3 would have given us that 7? What would have been in that empty spot? And if we think logically, 10 minus 3 would be 7. That kind of makes sense. So now let's go back and think for a moment. Oh yeah, that's right. This card had a 10 in it. And that's why. It's because the initial value of that sequence really is 10. The 0 term really is 10. The puzzling thing, and I'll admit this is a little confusing, is the fact that when you're looking at this green card, it doesn't give you that 10. Without a table, we have to know, and this is just vocabulary to know, that the first term in the list is literally n equals 1. The first term in the table is the first term in the list, n equals 1. Second term in the list, second term in the table. Third term in the list, third term in the table. When you are given the list, you're not really given the 0 term. By definition, a list starts with the first item, which is 1. So we'd have to go backwards in the list to find the initial value, and that's the 0. It's a little confusing, it's kind of weird, but it's something we'll get used to as we do more of this. So now let's take some time to just kind of digest all of this information and make sure that we understand exactly what these equations are all about. We now know that when we look at an equation, we have an initial value and an adder. The initial value is the number that we call n equals 0. So you can make a little note of that if you want to. The initial value is the one that we say is in the 0 spot in a table. And the adder is the number that makes the pattern grow. So now that you've seen that, take a moment and see if you can answer question letter B. I discussed it earlier in this video. So maybe you can either rewind or think back and see if you can answer question letter B. Does an arithmetic equation always have to have a plus sign? Are there certain circumstances where a minus sign might make sense in between these two things? Think about that idea. In the next video, we'll keep walking through more of these questions, but the more you can answer without watching the videos, the better, because that means you've made some observations that you can use.